Welcome to Instance Memory Acquisition Techniques for Effective Incident Response. That is a mouthful. I apologize about that long title. But today we're going to be covering a few different things related to instance memory. One, sort of as a kind of baseline for those that aren't familiar or might be newer to this concept, why is memory important? When should we collect it? What are the various acquisition techniques that we might leverage in the cloud? A little bit about the memory analysis process, a little bit of insights into that and what some of that typically involves, some tips and tricks, and then some key takeaways for this. So before we start, just a little bit about me. I've spent my entire career doing digital forensics and incident response. And here at AWS, I work in our professional services division, where I lead our threat detection and incident response offering development and delivery. And I help customers and partners like yourselves help build their incident response program and capabilities, leveraging my career of kind of doing this. So with that, let's get started. So first, why is memory important, right? Some of you might know it's important, we should be collecting it, maybe you don't, maybe this is the first time you're hearing about it, right? But one of the main things about memory is that it stores a lot of valuable artifacts that are not resident on disk or may not be resident on disk. For one, like running processes, what processes are running on your system. So if you're taking an image of a disk and you get that image and you're looking at it, you're not necessarily going to get information about what processes were running. You're getting an idea of the artifacts that existed on the system, but not what processes were running. Or what about network connections, right? So who was connected to the system at what time? Maybe there's historical network connections of who was connected from source IP addresses previously, right? Event and system logs. So there might be event logs or system logs that are in memory that haven't necessarily been written to disk based on how the operating system implements its mechanism of storing logs, right? So if you collect a disk and you don't collect the memory, it may or may not have written those event logs, right? So you may be missing out on what those things are if you don't have memory. Copies of executables. So executables that are run in memory will often be retained there, sometimes wholly, sometimes partly. Those can be very useful for understanding what the piece of malware might be doing. Command line history. Does anyone run Linux systems in their environment? All right. Does anyone know when Linux writes command line history to the disk? At what point? Does it write it constantly? When you run a command, does it write it to disk? No, right? A lot of times, most times, it'll keep it in memory, and it won't write that until that session closes, until you close that terminal, right? Or something else happens. So if you take a disk snapshot, an EBS, right, and you're looking at command line history that exists on that disk, that's likely not the latest set of command line history. So you're losing a massive amount of information of an attacker's moves, right? So very, very critical details, right? Deleted files that may be run, they no longer resident on disk. Sometimes these only exist in memory. Injected code from malware processes, a bunch of things, right? And I can go on and list, and this is really just even a small subset of what exists, right? So it's very, very important, right? So memory is something that is absolutely critical to our investigations. And sometimes it can be the only thing that provides us the indicators or details of that might be critical to finding out a root cause, right? So when we're looking at memory, right, some of these things like deleted on disk executables may be available for reverse engineering or analysis, right? So if we want to figure out what that malware was doing, especially if it was deleted and not resident on disk, this may be our only avenue to do that. If we want to look at historical connections of IPs to know who accessed that host, again, I mentioned the command line history, right? So a bunch of these things are super, super useful and valuable to us for our investigations, right? So I won't go on and on about it. Hopefully those are just a few items that kind of convey to you like, okay, what are the differences? I collected a disk, why would I care about memory? What is the information that we could have, right? Tons of stuff, okay? So now we kind of hopefully agree that it's valuable. We can definitely use that stuff in our investigations and maybe we're realizing, oh, we're missing out on a bunch of stuff, right? So great, I'm convinced it's valuable, right? But when should I collect it? There's a variety of different situations in which you can collect memory. Here's a few. This is not an exhaustive list, right? But you could have predetermined situations in which you collect memory, right? So maybe you're not going to collect it for every single system that might be compromised or that you want to investigate. Maybe for high-profile systems, particularly important web servers, right? So you may have like a predefined list if you maintain an asset database of like high or critically important servers or systems, right? You may, at that point, if those are compromised, that may be a situation in which you collect memory. Not necessarily from hundreds or thousands of other systems, but from a certain targeted list, right? Of course, that requires you maintain an accurate list of assets and and manage those effectively, which everyone does, right? 100%? Absolutely. All right, great. or just one time, right? So this may be an ad hoc process. You don't necessarily collect it all the time, but if there's a particular situation or possible compromise or a security incident which merits, maybe you think you're gonna need additional analysis outside of just having the EBS snapshot of the volume, maybe you say, we just do this as an ad hoc situation, right? Or as a standard practice. You could implement this as part of your standard response process, right? And that's totally okay. If you do that, you're also gonna have a mechanism to ensure that you effectively manage this collection at scale. Where are you gonna store all this? How are you gonna effectively name them and manage them, that sort of stuff, right? So there's a variety of situations in which you might want to collect memory, right? And there's no one right or wrong one. This is just kind of a balance of your business operations, what you're looking to collect, how you're looking to collect it, and what value you're looking to drive out of this, right? So when we're talking about collecting memory, no matter what situation we're looking to do it, there's some considerations we need to have, right? So it's valuable information. We definitely want to start collecting it in certain situations. But the thing about memory is data is constantly changing. Data is constantly changing on disk too, but particularly so in memory. And there's a variety of actions that we want to avoid so that we don't trample over memory and overwrite some of this valuable information or effectively remove it, right? And so situations in which we might affect memory is system activity. So if we perform actions on the system, right? So even running a memory collection utility will affect memory, right? So we're running it, it's gonna be loaded into memory, it's gonna affect memory, right? But there are some necessary actions we have to perform, right? We can't totally avoid altering memory at all while also collecting it most of the time. Also, network isolation. So how many of you have a process for responding to possibly compromised EC2 instances? All right. And how many of you have isolation or quarantining or containment as part of your processes? Right? Okay. How many folks contain or isolate before they collect an EBS snapshot or memory? Right? Okay. So if you perform network isolation and then you collect memory, you're going to lose active network connections as part of your memory collection, right? So you've contained it, those active network connections are going, I can't connect anymore, and they drop out of memory. And then you collect memory, and they're no longer there. So how would you know what those connections were? You've lost the data, right? So it's really, really critical to understand that some of our actions impact memory, how they impact memory, and that order matters for all of this, right? And memory is volatile, right? So this can be, as soon as we shut down a system, memory for all intents and purposes is gone, right? So in understanding all of these things, that our actions and what we do can impact it, and that there's valuable data, we want to operate in the most effective way to where we collect the most amount of data possible while having the least amount of impact, and the order of operations very much matters for that. So what are those order of operations, right? So in AWS, we have a methodology called EBS snapshots, where you can simply just click and collect a snapshot of a disk, right? And it goes on behind the scenes. It doesn't depend on you waiting there for you to finish it. It just happens behind the scenes, right? Very, very useful functionality, right? So that's obviously one of the first things you want to do. Very, very low impact, or almost no impact, ostensibly, and we've got a full disk image, right? Then we want to acquire memory. So what would happen if we tried to acquire memory first? Nothing, if it goes well. Has anyone tried to do memory acquisition and accidentally blue screens a system or terminates it or shuts it down, right? These people have done memory collection. They know, right? Like, this stuff happens. If I do that first and the system shuts down, that alters disk artifacts. So I want to make sure I have those disk artifacts before I do that in case that situation happens, right? So order very much matters, right? Disk snapshot, memory collection, right? And then we've got both disk and memory. We've got most or all of the data that we need. So then we could do some live response or artifact collection if we need to do it. I don't necessarily recommend doing that. Typically disk and memory is probably all you need, but if you have a good business use case and you say, I want to poke around on the system, we want to run some live collection utilities, okay, you're positioned well to do that because you've already got a snapshot of the disk and you've got an image of the memory. You're not going to alter those back in time. You've already collected those, right? And then we can go on and isolate and contain the system, right? So we don't worry about altering memory because we've already collected it. We already have those active network connections. Now we can isolate and contain the system. And then it's a responder's choice based on situations or goals, right? You've got the disk, you've got the memory. You should probably just shut the system down, right? There are situations where you may want to leave it up for monitoring and interaction. I would just highly suggest you very much know what you're doing, and it is effectively isolated if you're going to do that, and you have a very good business case to do that, right? So one of the major things here about isolating and containing a system is how many people are attempting to isolate and contain their instance using security groups? How many people are isolating and containing systems using NACLs or network ACLs? Okay. How many people are containing using an EDR agent? Okay, a good amount. That's actually a very effective way to do it on the host. So how many people are aware with security groups of connection tracking? Does anyone know what connection tracking is? How security groups work? So it's a really important part of security groups. So connection tracking, there's tracked connections, there's untracked connections. I won't go into all the details of this, but if you implement a security group with no rules, you will prevent future connections, but you can't necessarily terminate all active tracked connections. If a connection is tracked, that connection will sustain even if you remove all of the security group rules and attach a security group with no rules, just by how tracked connections work. Highly suggest you look up how tracked connections work. Very, very important to understanding security groups in isolation. At any rate, while you can't effectively terminate active connections, you can prevent future ones by attaching that security group and isolating that system, right? Something to take into consideration. But for all intents and purposes, we've effectively collected disk, we've effectively collected memory. We should just decommission and shut this down, right? But the order matters, right? And we need to collect memory, the big takeaway, prior to doing anything that affects the data that resides in memory, right? Major, major takeaway, right? Then we discussed that. Memory acquisition techniques. So what are some of the techniques that we might use to collect memory, right? So memory is important. There are considerations and caveats. There's a specific order that very much matters to make sure we're collecting the right data and not overwriting it. So what are some of these prerequisites for collection? So again, minimize interactions, including responsive measures. We don't perform isolation prior to acquisition, right? Major takeaway. We need to establish an external collection target. We don't want to be writing memory to the source disk of the compromised system that would overwrite data on the system, right? So we want to make sure that we have some external collection mechanism and capability to when we collect this memory, we're writing it out there and we're not writing it to the source system, right? And so that means we need to pre-instrument some of these targets with connections to these external things, like we maybe write it directly to S3, and we need to pre-instrument the targets with collection utilities. How are we going to collect this memory without a utility to do that, right? So we got to figure out how that happens in anticipation of this, right? So first is a traditional technique for collecting memory, right? So several folks have said they use EDR. There's probably memory collection utilities built into that, maybe, maybe not. But these typically rely on deploying the agents to their endpoints, right? So it's a program that just runs and listens for commands, and you would invoke this, through your console utility. And this facilitates the memory collection. And so a lot of that is handled through the agent that's already running on the system. And typically these are deployed at launch time, so you're not ad hoc deploying them, but you could deploy them ad hoc. And this is traditionally how things have been done with physical systems, right? So you'd have these agents because you maybe they were located somewhere else or you couldn't reach them or they're easier to manage at scale. You'd use these agents. This is how you typically collect memory. And it's worked for a long time, right? So some of the pros, multiple commercial options and tools available, right? This is not a new concept. A lot of options for these utilities. The process of collection could just be a simple few clicks through your console utility. Tried and tested. We've been doing this for a long, long time, right? Before the cloud even existed, right? Some of the cons or considerations, so you have to have an agent pre-installed or you've got to install it post-event. I don't have a very good feeling about having a compromised system and trying to install an EDR agent post-compromise, right? I don't know about the success of that. We're running some real risks there. One, how's it going to interact with the malware? Is the malware going to allow it? We're interacting with the system, so we're changing stuff on disk, right? It's just, there's a lot that goes into that, not the ideal situation. So it requires purposeful setup to make sure that we have those installed, and we've got network connectivity to get that memory image out of there, right? So we can request it to get out of there. How do we balance this with containment, right? How do we make sure that that has the right, connections to wherever we're taking this thing? Risk of driver and kernel issues, again, with any memory collection utility, there is a risk of running this because it interacts with the kernel to try and collect all of the available memory. And again, we've got to pre-configure that instance connectivity to external storage for writing memory, and don't run it to the disk. There's live collection. So we don't have an agent running or pre-installed. And what we do is we would just frankly, directly connect via SSH or RDP to the instance. And we would either have some utility, maybe we'd have a utility loaded on there at runtime. Maybe this is part of our CI/CD process, ideally. We don't want to, again, load something at connection time onto a system again we want to mitigate the amount of artifacts that we're affecting. So we might copy it over runtime, not the ideal situation, but if it's not on there already, we have to do that. And then we'd have to have access to some external location to write that. We'd manually run this collection utility. So this is not uncommon, especially if nothing's pre-instrumented, right? We would manually connect SSH RDP. We'd maybe SCP something over there, somehow transfer it. We'd get it on the system. We'd run the utility and collect it. It's a little bit kludgy, but it totally works, right? It's a great backup mechanism, and it is a technique to do that. So some of the pros, like no deployment agent overhead. I don't have to worry about, was this agent deployed ahead of time? Is it throughout my environment? Are we sure it's on this system, right? And we get direct access to the system through SSH or RDP, right? And again, something that's been used for a long, long time, ad hoc collection. So we just live connect to it, transfer utility over, and we collect the memory. It works. Cons, again, risk of trampling and affecting artifacts that exist on disk and memory, right? And this alters and complicates artifacts. So if the situation is where an attacker compromise the system and they're connected and they're SSH'd in, there is that command line history, maybe that they're running and doing whatever. And now I'm connecting in from another SSH session and I'm running some commands, and our forensic analyst is trying to discern whether the attacker running these commands, these files are changing at this time, but you were also connected at the same time and you were collecting memory. And so it kind of munges these things and makes things very, very blurry and unnecessarily complicated for our analysts, right, to do this investigation, try and figure out what the attacker was doing versus what we were doing, right? And when we do this live interaction, this is kind of the stuff it introduces, right, which we really want to mitigate. And again, we've got to have pre-configured instance connectivity, right? So we've got to have access to that instance. We've also have to have access to write that memory out to somewhere, right? So like we've seen before. Now some cloud-focused techniques, right? So getting into AWS Cloud and using AWS Systems Manager, right? So what about instrumenting configuring Systems Manager throughout your fleet to be able to connect to your instances and run this memory collection, right? Totally viable option, right? And Systems Manager has this notion of documents where we can have these pre-configured commands and we can run all of these by invoking a SSM document and having it run this predefined set of commands to run collection, right? So there's a run shell script, there's a run interactive command, there's run custom documents, and we can build these to automate a multi-step process, right? So if we're leveraging SSM, we need to make sure that this memory collection utility is available if we want this document to run this collection utility at runtime. So it's either, again, got to be resident on the system, it's got to be copied over at runtime, or it has to be available somewhere for us to acquire it and run it on the system. Perhaps we can run it from some external target, but it has to be accessible to SSM for it to run the document and do it. And so through SSM, AWS Systems Manager, and through an agent, we can issue sometimes just a SSM run command and we invoke the memory allocation. It's really quite an effective way to do this, right? So from a perspective of pros versus cons, what are the great things, what are some of the considerations, right? So it's a native system or native service capability, Systems Manager, right? It exists in AWS. Simple method for collection. We can do a run command. It can use existing tooling on the machine, presuming we bake those into our AMIs as part of our CI/CD process, right? So then we're not copying anything over at runtime, right? So we can just invoke SSM, run the commands. If we're using containers, we can use ECS exec for running commands on containers, and it can be automated, right? So we're starting to get in the automation part of this, which is really, really leveraging the power of the cloud, right? So we're using a native service and automation, right? Some of the considerations, right? Obviously requires pre-configuration and deployment of Systems Manager on all instances, right? This is not necessarily, a one-click and it's everywhere thing. It's very purposeful. You've got to figure out how we deploy this throughout all of our environments, right? So it does take purposeful setup. It requires additional tooling to be preloaded or loaded at runtime, right? So if we're using SSM, we say, hey, go do this, right? If that memory collection utility is not baked into that AMI, then again, we're gonna have to copy it over at runtime and figure out how we do that as part of the process. And again, like we've seen before, we have to have connectivity to external storage to write that memory out to somewhere because we don't want to write it to disk, right? Now here's a technique that I'm currently researching as has worked traditionally. What about using Hibernation to collect memory, right? Has anyone used Hibernation in traditional physical systems, right, to acquire memory? or just as a mechanism of operations, right? Either or, right? So traditionally, I've used this as a technique from physical infrastructure in previous days of doing incident response, and it's a great mechanism. And Amazon EC2 has a mechanism in the service to enable and configure hibernation and to hibernate your systems, right? But we got to understand the prerequisites and caveats if we would like to leverage this, right? So there are limitations, always increasing, even from just a year ago, ever increasing support, which is great. But there are specific limitations for instance type, AMIs, and RAM. You can't activate it for ECS instances or auto-scaling groups at the moment. That may change in the future. Again, we're always improving and adding capabilities. You can't configure it to hibernate an instance that is in UEFI boot mode, which is a consideration to take into account. Has to be configured at launch. So we can't go and say, oh, well, a system's running, wasn't configured for hibernation, but we'll configure it now and acquire memory. Doesn't work that way right now, unfortunately. So it has to be configured at launch. We have to know that ahead of time, right? So it takes purposeful consideration. Acquiring a snapshot may render the instance unreachable. So that is a bit of a risk that is a part of this. But something to take into consideration that we build into our playbook if we're going to leverage hibernation as a mechanism for acquiring memory. And there's more. I highly recommend you look at the documentation, but totally viable method. There are considerations if we like to use it. So configuring them, we configure it at launch. It's sometimes as simple as just the checkbox, or you do it via the CLI or whatever you like to do. And we have to ensure the root disk is encrypted and large enough to hold the contents and size of memory, right? So if the root disk volume is too full or the file hasn't been allocated with a large enough size, and we go to hibernate the instance and attempt to write that 8 gigs of memory to 6 gigs of disk space, it's not going to do it. It's not going to write 6 gigs and go, well, I wrote 6. It's just not going to do it. It's just not going to collect it at all, right? So that's something we have to take into consideration, make sure that we have and maintain sufficient space on our disk if we're going to leverage this as a mechanism, right? And so in that mechanism, we just leverage hibernation, assuming we've done the prerequisites and caveats, to write the memory to disk. So what are some of the pros and cons of this? Again, another native service capability, right? So built into Amazon EC2. Simple method for collection, not that we should be doing everything from the console, but to demonstrate the simpleness of this, right? You can do the same thing from the CLI. You can do a stop instances and enable like -- hibernate, right? And hibernate the instance. One of the upsides is doesn't require external storage. So all the previous solutions were like, okay, we're going to acquire memory. Where are we going to write this thing? How are we going to get this thing out? We got to have external storage pre-configured. Is that large enough? Does it have access to it, right? So one of the pros of this is it writes it right to disk. But you're like, shouldn't we not write memory to disk? You've been telling us not to write memory to disk. Well, the way hibernation works is it pre-allocates space on the disk for this thing to be written. So it's not like we're overwriting log files that might exist somewhere or anything like that. It's this file, and it maintains the space for it. And so when you go to hibernate and shut the system down, it just writes it to that space that was dedicated and allocated for this. We're not overwriting other things on the system, which is great. So in this case, we are okay writing that to the system volume. Not us, we are actually writing it. The system is, because it's pre-allocated it, but it's purposefully built for that. Some of the considerations, like we went through, has to be configured at launch. Collection runs a risk of making it unreachable. There are some memory size limitations, which I put on there. Currently, Windows has to be less than 16 gigs, which, if you have instances running larger than 16 gigs, you're not going to be able to leverage hibernation, unfortunately. That limit is much higher on Linux instances, which is great. And again, the root volume must be encrypted, and there are several other caveats and considerations. I will say, keep referring to the docs, again, because they're always being updated. We're always reducing those limitations and making this better. But as a possible means of collecting memory, again, which I'm currently researching, this could be rather effective, right? Native service capability, don't have to implement external storage, right? So things are looking good, and hopefully more developments in that space as time goes on. So we've covered it's important, caveats and considerations, techniques to do it. Now let's get a little bit into memory analysis, right? So let's talk a little bit about what is memory analysis. And let's start with what are some of the formats, right? So memory can be acquired or stored in a variety of formats, and it can range from raw or padded, as it's referred to. So there's no headers, metadata, magic values, other things that might be populated as part of other formats. But it's just essentially with non-system areas padded in zeros, it takes a raw image just straight from how memory exists on disk and writes it, right to wherever you're collecting it. There's also core dumps. Anyone else had a system that accidentally halts or does a core dump and it says, I'm writing the core dump to this system or whatever, right? So contains memory. Like, that's valuable information we can use. Like, sometimes you purposefully want to do that to acquire memory, right? Not a lot of us have done that purposely. Usually it's from an accident of something we did or some program did, right? But this is, it stores in an ELF format for Linux and the variety of things for the different types of operating systems there. But sometimes we can leverage a core dump for memory analysis, right? And a variety of compression formats for when collecting memory. And so there are a variety of different memory tools. We'll hit on them in a little bit, actually on our next slide. And they use a variety of different compression mechanisms. And so Encase, which is widely popular for acquisition and forensic analysis, has used bzip2 or LZ. Anyone notice those EWS formats, EWF-E01, EWF-EX01, right? That's if you're seeing that and you're familiar with that, like that's typically the format that it'll collect it in. If you're using native utilities to collect memory, you can use native encryption. You can use zip, gzip, tar, right? So there's a variety of different compression mechanisms and utilities and formats that we might encounter when acquiring memory. And that's all to say just to be familiar with them, right? So it's to say a different tool might collect it in a different format. You might have options to use varying compression formats. It may be compressed, it may not be compressed, right? And the format matters, right? Because you have to know the format that your tool that you're going to use or tools are going to use can handle that, or that they can convert it to the appropriate format. So speaking of tools, there are a variety of tools, and this is in no way an exhaustive list of them. This is more to just socialize the amount of tools that are out there. So we have open source utilities like Lime, AVML, we have the PMEM suite, we have Access Data's FTK, Magnet, Belkasoft, Encase, more, right? And so again, different output formats, different compression methods, and that matters when you're going to do memory analysis, right? Now, when we acquire memory, we might write it to disk, right? Or we might store it somewhere else. Write it to disk if we're using Hibernation. But if we are writing it to S3, if we're writing it to an external bucket, right? If we used SSM to write it to some external target, right? For access for analysis, we might just copy that to our local forensic analysis machine to the analysis. We might directly access that drive from a map volume to S3 if we're going to use a real-time interaction with a file system. Maybe it's mapped to an EFS system that we can live connect to and interact with. If we collected it to an ECS or an EBS volume, like for Hibernation, so say for example we leveraged Hibernation and we hibernated the system, it wrote it to the root volume, how are we going to access the memory that's on that volume? Well, you can attach that volume. You can create a volume from that snapshot, take a snapshot of that root volume with the hibernated memory, create a volume from that snapshot, which would mimic the original volume, then attach that volume read-only to an analysis system and directly access the memory that's in the Hibernation file that way, right? So there's a variety of ways that we would access these things depending on how we collected them. So what tools we use for analysis? So there's acquisition tools, here's how we'd access them. What about tools for analysis? So Volatility or Volatility 3, which is the latest iteration, is one of the most popular open source tools that people leverage for the community, built by the community to do memory analysis. Anyone heard of Volatility? Yeah, a lot of people. Very popular, right? Recall, I don't believe that's maintained anymore. It might still be maintained under GRR. But anyways, some of these collection utilities also have the ability to do the analysis, right? You got the FTK, Belkasoft, Encase, right? Some of these more commercial options utilities, they're gonna say, hey, if you collect it, we also want to help you analyze it, right? So we've built that in, it's part of our commercial tool, blah, 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 right? So some of those have the corresponding things. You may not have to worry about what formats, that Encase is in EWF-EX01, and what does that mean or how, because Encase says, well, we just parse it for you, right? So you don't necessarily worry about that with some tools. But you do need to be aware what those formats are in case you don't have that tool, or use a different tool for acquisition, or you want to try other tools, or you want to look at, the structures of this memory, right? So diving a little deeper into memory analysis. So there's acquiring memory, there's the formats in which it might exist, there's compression, non-compression, there's core dumps, there's tools to collect it, right? So we collect it, it's in a certain format, right? But we want to do the analysis. Well, critical to the memory analysis is the tool understanding where information is located and what maps to what in this image that we've collected of memory, right? So we have this notion of memory profiles or symbol tables. And so these are required for performing analysis of this image that we've collected. Some tools have an existing repository of these profiles. Some automatically do it for you behind the scenes. And some require you to generate your own profile or symbol tables. So if you're required to generate your own profile or symbol tables, like for example in Volatility, there's a repo of some profiles and they have some symbol tables which you might need to generate your own, right? That's going to be up to you to figure out how to do, right? So it's an open source tool, it's an open source utility. We help you as much as we can, but we can't do everything for you, right? It's not what the tool is built for. So you have to have an awareness of, if I use certain tools, some more work may be required of me. Once I acquire this thing, I can't necessarily just plug it in this tool and it works right off the bat and I get every single piece of information, right? Because different systems have different versions of things, different kernels for Linux, right? So to build these symbol tables or build these profiles, you're gonna need to figure out how you get access to the kernel file or headers or debugging tools like on a Linux system to build those profiles, to be able to build that, to point volatility to or whatever tool to say, hey, here's we collected this image, here's how to parse it because this is the symbol table or profile that I built from a representative system, right? And here's how to do it, right? So methods for doing that, methods for generating memory profiles or symbol tables. So there's a couple ways to do it. One is on the target of the compromised system. Is this the ideal way to do it? Absolutely not, right? Especially if we're talking Linux as an example. We have a possibly compromised system, we've got a security incident, we have no idea what's going on with the system, we have no idea what is related to this incident yet, and we don't know what artifacts exist on the system or what we might need to analyze or have access to, right? And we don't want to go on the system and say, oh, install kernel header files and install all of these core compilation tools, and just start obliterating the disk essentially with all of these updates and things that we're doing amidst an incident, right? Amidst possible attacker activity. They may be actually connected now as we're doing this, right? Definitely don't want to do that, right? Sometimes it is a last resort, right? Sometimes we have no other way of doing this, but it's not optimal. It is a method, but not optimal. Ideally, we have a replica system. So if we're thinking replica system, we're thinking, how would we do this, right? So to generate a profile or a symbol table, again, using Linux as an example, if we are running, Ubuntu with kernel 4.5 or whatever, we're gonna need that same kernel to generate the appropriate profile or symbol tables, right? So the target system clearly has that kernel because it's running it, but as a best practice, we wanna stand up a replica system with the same kernel, the same operating system, the same exact structure as best as possible, generate a profile and symbol tables from that. Again, we control the system, it's not compromised. We generate that profile and symbol tables, then we can use it to parse that memory image that we've acquired from the target system, right? That's the ideal situation. Now, some of you may be thinking, okay, great, so we generate this from a replica system. Maybe we're thinking, great long-term, we're gonna integrate this into our CI/CD pipeline. And every time we have a new image built or something, we're gonna automatically generate a profile, and we'll have that at the ready to parse our memory images that we collect from all of our systems. Can we think of a situation in which that might not work? Ideally, if this was an interactive session, you all would be able to answer and give me ideas, but I'll just tell you what the situation is. Some of us have systems that have been up for a while, a month, a year, 2 years, 3 years. It might have launched with kernel 4.1, and it's got kernel 4.6 now that it's been upgraded to. So if I built that profile as part of its initial launch, I don't necessarily have that profile for the latest kernel version that it's running, right? So one of the things we will have to do as a mechanism of generating profiles and symbol tables is we're going to need a mechanism to figure out what kernel is that system running, right? Or what operating system is that system running? And this applies to everything, and not just Linux, Windows too, right? What latest update from Windows is it running, right? And that affects the profiles and symbol tables that are available, and that we'll need to build to process that memory image file, right? So some considerations here, right? Ideal on a replica system, last resort of the target, right? And considerations that over time these things may change even if we build them into our CI/CD pipeline. So some considerations to take into effect when we're building these profiles and symbol tables. So we've built them, and let's say that's all gone well and gone swimmingly, and we've got a replica system and we've built the target profile and symbol table. Has anyone ever done that and it just didn't work? Yeah, so sometimes that happens. So we have a representative system, or maybe even on that target system, somehow we built that profile and it doesn't work. You want to find that out before you shut that system down, right? So especially if I've built this on a replica system and it doesn't work, and I have this target system and I'm going, it's not an ideal situation, I shouldn't be connected to the system, but I've stood up a replica, I've built the profile, it's not able to effectively parse the memory image from that system, I want to know that before I shut that system down, because sometimes, again, that last resort might be, I might have to connect to that target to build that memory profile of that exact system as it's running, because me doing it from a replica just isn't working, right? And you don't want to find this out after you've shut the system down. Memory's gone, right? Or maybe you have acquired memory and we shut the system down and like, okay, so we are good to go. We've acquired it. Maybe we can stand it back up in isolation and generate a profile from that and do it in a much safer way, right? So creating these things isn't really the last step, right? We want to test and make sure that they work before we kind of complete this process of shutting the system down and kind of moving on and doing analysis, right? And sometimes it might take multiple tries to go back and rebuild this thing and figure out what's missing or what's not working, right? So it might take multiple attempts to do this. Something to take into consideration if you've never built these. Sometimes it can go exceedingly well that you scare yourself how well it worked, and sometimes you think you're an expert and you're like, I cannot figure this thing out whatsoever, right? So again, from career experience, follow some of these steps, verify it works before we, terminate or get rid of these systems, right? So just some tips for performing analysis, right? So going back over some of the things that we discussed. Understand your memory formats and profiles, right? So sometimes we may build a profile or symbol tables, and it may effectively parse the memory image. We may get output that just doesn't look correct. And sometimes profiles are available that we use. This is particularly common in Windows situations. So you may be using a profile. It's a Windows, let's say 2012 server, and this is a 2012 profile. I'm like, this thing should work. And you're like, I got the profile, it's pre-built, and I plug it in, and I go to do, a process listing, and it just outputs garbage, right? Well, why is this not working? Sometimes using the 2016 profile works. Why? Sometimes I don't know. I mean, sometimes you just realize you made a mistake, maybe they made a mistake, right? But you need to be aware that if you're getting misleading or erroneous output, it might mean you may have to build another profile yourself, right? Understanding your tools, configurations, and limitations. So some tools can be figured to speed up processing time. And so using volatility as an example, there's some special flags that you can provide. You can run a certain utility to gather some information from the image to acquire the KDBG address and DTB values. And you can input these at runtime. And so anybody who's tried to do memory parsing or processing using volatility, I don't know if you're aware of these things, highly valuable. And these drastically speed up your processing time. So if you've ever noticed, you go to process a memory image and you hit, here's the plugin, and you press enter, and you wait 10 minutes, and then you go, oh, I put the wrong thing in, or I need to run this again or do whatever. You don't want to hit that button and hit 10 minutes again, because what's happening behind the scenes is volatility is trying to go, okay, where are these things located? I have to manually parse through the whole image, but if you just provide these addresses to me, I can drastically speed this up, right? So just knowing your tools, and that's just one example of volatility, other tools have similar things, but just knowing your tools and their configurations, limitations can drastically speed up your process, especially if you're doing this at scale. And work smarter, not harder, right? So you don't always necessarily want to go through and manually inspect an image and go, which process is related to what, and look at the process tree. Well, what about using golden memory images or AMIs from AMIs for comparison, right? So if we have a standard AMI we deploy, we know what tools and utilities are running, a standard part of our servers, right? Maybe we acquire a memory image of that, and we use that as comparison for when we're doing our analysis. So we don't have to go through every single process and not know, is this right, is this wrong, is this unique, is this not right? Work smarter, not harder, right? And build automation, parse and extract this pertinent info, right? So again, using volatility, I just have a lot of experience using that. You can build automation to go in and extract those KDBG, DTB values, provide them at runtime, do all of that behind the scenes, run all of this processing and plugins and stuff, and have all of that output it to a folder, so your involvement only starts after all that's been done. So we're not just paying you as a very smart human to hit the button and wait the 10, 20 minutes to parse this every single time, right? So figure out ways that you can really build automations and scale this analysis, throughout your environments. So key takeaways, if we can just narrow it down to just a few. Memory is obviously a valuable resource, right? So if you hadn't heard of it before, or you weren't convinced or something, hey, maybe that's the major takeaway that you take away from this, right? And sometimes it's the only available source of artifacts for your investigations. So it is not uncommon, in my experience, for memory to give us very insightful information that we could have never learned from just acquiring a disk image. As part of our operations in our organizations, we want to implement a standard methodology for acquiring memory, right? Whether it's ad hoc, whether it's for certain servers, right? We want to make sure this is a repeatable and scalable process. We want to build our methodologies and workflows, right? So from integrating these memory profile creations into our CI/CD pipelines, We want to build workflows maybe for automating some of the initial parsing, right? That's key to doing this at scale, right? And to drive the most value, it must be collected and parsed properly, right? So not collected after isolation, right? Collected before isolation in the right ways and minimizing interaction with the system, right? And so as part of our process, if we're gonna get serious about implementing memory acquisition and analysis, we're gonna need to implement some sort of methodology to research, build, test, verify the life cycle of acquisition, our tooling. Sometimes you get tooling updates, sometimes you wanna test new tooling, maybe you can do things a little bit better, faster, different, or you just wanna verify that your initial tool is right. And keep in mind, these things are changing all the time, right? And so there's a reason that we need to constantly generate new profiles and new symbol tables and stuff, because the operating systems and artifacts are constantly changing. It would be great if we just had one profile that was Linux and it did everything. We had one profile that was Windows, right? That would be amazing, right? But it's just not the way it works, right? Just by nature of how memory is acquired and analyzed, we need to understand how those mappings are changing, right? And so it's a process and we're gonna need to stay up to date on it. It's not a set and forget and we built that last year and it works. No, we need people dedicated to this process, right? And it's better to identify process adjustments before they cost you valuable information, right? So we have a process that always builds profiles and it's always doing it in the background, and a year goes by or 6 months go by and we want to collect memory from the system and then we go do it and we shut it down and we blow it away and it was this weirdly configured system and we never want to do that again because it was super old and we have a new AMI from it and the profile doesn't work. Well, we should have identified that way earlier in the process, right? Not after we blew everything away, right? And just expected it all to be working the same as 6 months to a year ago, right? So some key takeaways, obviously more than that, but if we can distill it down to that, right? So if we've helped convince anybody that memory is a valuable mechanism to start collecting today, please raise your hand. Yeah, decent, right? So who was already collecting memory before any of this? Who wasn't collecting memory before this? Whose view is completely unchanged? In a good way, I hope. All right, excellent. Maybe we just reiterated the value of this and have some additional mechanisms for you to do that. That's largely my presentation, so I thank you. I've gone through it at a pretty expedited rate, but given it's a silent session, I don't think I can take question and answer here, but I will be happy to stick around afterwards and talk with everyone and curious about how your methodology is working and what works for you and what doesn't, and just happy to answer any Q&A. So thank you very, very much for attending. I appreciate it and hopefully see you at some of my other sessions. Thank you.